Okay, so once again, good afternoon to all of you. And thank you for joining this class on a Saturday. And today we'll cover another topic on what we have been discussing, agent-based modeling. And in that, we were talking last time about the search methods. And today we'll cover two aspects of search methods. One is called the breadth first, and the other is called the depth first. So as some of you said earlier that you may have studied these as part of your algorithm course. So I'll take some of your inputs when we cover this. Sharing my slides. Okay, so we last time earlier in one of the earlier classes, we also discussed what is an informed search and what is an uninformed search. So uninformed search is when you do not know whether you are getting any closer to the goal or not. So you're in such a situation, what you have to do is you have to search a tree in such a way that you cover maximum, you have the maximum coverage of your search, and also be able to reach your goal state as soon as possible. So how in such a scenario, how do we expand our tree? That becomes critical. How we expand as we go to the frontier nodes and which node to pick for further expansion. So there are three methods for doing this. One is called the breadth first search method. The other is on the other extreme is depth first, and in between there is one important point where we consider the cost versus the number of actions, that is uniform cost method. So I'll discuss these three today. So first of all, the breadth first approach, as I think broadly we understood it last time, that when we are trying to expand our graph and we use the terms like frontiers, expanded nodes, and the reached nodes, and the current node. So can anybody remind me what would be a breadth first approach for such a search method? Because we have already done briefly in our previous classes and you have studied in algorithm also. So let me take your inputs. Can someone define what is a breadth first approach? Please come forward and participate in this. Come on. Yes. Who is speaking? Pushpak? Come on, I'm waiting. Some of that is written here, so perhaps you can combine this with what you already know from other courses. So you just define to me what is breadth first approach of searching a graph. What kind of search tree will we create in this? Then there are a few points that are written on the slides. We'll discuss these points about this search. First of all, how will you proceed? Suppose you have a graph, and let us say you have a graph which has been arranged in a rectangular way. So you have certain dots connected in a square, in the form of a square, just like your graph paper used to be. So on this graph, suppose every intersection between these grids represents a node. So how will you proceed from, say, top left node to start searching for the goal state? So just tell me in a natural language, how will you proceed from here? So if you can't come forward, then I will ask you individually by name as they appear on my screen. So please come forward and just be participative. If you know, then it is fine to repeat it here. And if you do not, just try it on your own. I mean, if you have even not heard it before. Okay, let me ask individually then.
Is this breadth first approach same as that we use in graphs or trees?
Yes. Yeah. So say again. I couldn't hear you.
Is this the same breadth first that we use in traversing graphs or trees.
Yeah, we are looking at graphs only. Yes, we are continuing with that.
Yes.
Mhm.
So, sir, in that way, given if we are given a starting node, we first look at all the nodes that are connected to that particular starting node that at the same level. Once done with that connections of the first node, we maintain a queue. Now the first neighbor that we chose from that starting point is chosen, and then we select all the unvisited nodes of that particular node. Again, that is posted out, and it goes until we traverse the whole graph. It's level wise.
Yes, excellent. So what we have, for example, I am at a current node. I gave you example of a graph, which is a square graph, where I have grids, and every intersection represents a node. So suppose you are starting from top left. How will you go? How many points will be connected? How many nodes will be connected to this? How many nodes are connected in such a graph where I'm just the grid, a mesh kind of a graph, rectangular? If I start from top left, 2 will be connected. Unless diagonal is also connected. So it will be either 2 or 3 if I represent this. So let us say 2 nodes are connected to my current node. So in the breadth first approach, which node will I expand after this? And then subsequently. I mean, you already answered. It's just I'm repeating from there.
Sir, any of those two nodes connected to the first node?
So yes, so there, as far as the breadth first approach is concerned, it is not, you don't choose out of which these two which will come first, right? So in this case, you will just say there are 2 nodes, and all these 2 nodes will be kept in the memory. And then each of these 2 nodes are also called frontier nodes, and they have reached nodes for now until you expand them, and now you expand them. And then 2 of them will be expanded, and if each of them is connected to 2 further nodes, so then from 2 you will go to 4. So in the first stage, as you rightly pointed out, we will just expand both of them equally.
And sir,
so yeah, yes, Priyanshu.
so we will have to maintain the visited array so that we can find
Yes,
so repetition might not happen.
yeah, this is a very important point, and that is what we will see will be the limitation of this method, because you have to really keep a lot of information in memory. So its memory complexity of this method is high. So we'll come to this point. This is an important point though. So, but the order of expanding the tree is that you expand all the nodes which are connected to this, and then you further expand the next level, and then as soon as you reach the frontier, so the number of nodes at a given time which we are trying to expand will remain constant, or will it grow? In a uniformly connected graph, such as I mentioned, such a simple grid, square grid, or lattice-like structure, where every node is connected to 2 more nodes in one direction. And in fact, if it is not directional, then it will be every node will be connected to 4 nodes, 2 backward and 2 forward. So if it is directional, 2 nodes can be connected to this. We know this type of a graph has a particular name. I'll come to that soon. So in this way, at a given time, first I had 1 node, then in the next step, I will have 2 nodes. Then these 2 nodes, as I think one of you have written in the text, Karthik Ohri. So increase at each level, yes. So you understand that the graph will keep on expanding, the memory keep on expanding, or amount of number of nodes that you have to expand at a given time, or the size of the frontier that continues to grow. And that continues to grow until the last node is reached, or that will start shrinking at some point. So if my graph is a finite graph and like a finite lattice, at some point of time, my frontier will start shrinking because the number of connectivities will start reducing. But if it is an infinite graph, then my number of nodes at any given time in the frontier will continue to grow. So this is the first aspect of the breadth first approach, that we are looking at the breadth. So what does breadth mean here? So breadth here means the number of nodes which are part of the frontier. And you are keep on expanding the frontier. So it is like your going like the waveforms as they proceed. Then second is, now if every node is connected to say n nodes on the frontier, this question can also be asked, which one should I try first? So that why I have to try more than once is because one of these nodes on the frontier may be a goal node or maybe represent a goal state. So what is the fastest way to search this? So what we do in this case, we implement a kind of a queue, and the queue will be first in, first out. So in that way, you do an exhaustive search. So first node that comes in, you test it, whether it is a goal node or not, and then you will do other operations, and then you go to the next. So as I discussed earlier, whenever we are doing a search method, we have to look at this question. Is this method guaranteed to give me the optimal solution? So last time we just discussed, we have to look at the optimality of the solution and complexity of the solution, and two kinds of complexities we talked about. So the first question is optimality. So what do you think a breadth first approach of searching a graph, does it guarantee that a solution will be reached? I'm not bothered how long it takes, but does it guarantee a solution?
Yeah, it guarantees.
It guarantees a solution, right? Because you primarily scan entire search space. So breadth first approach guarantees that a minimum path will be approached. Then there is another question. So if I have to define the evaluation function, because now in the abstract sense, every search method that I'm introducing, we said that every such method differs from one another in terms of what evaluation function I'm using. So can you guess what is the evaluation function here? Can you recall what is the evaluation function and how is it different from the performance evaluation? Just recall it. What is the evaluation function?
Evaluation function tells us which of the frontier nodes nodes to expand upon.
Yes. So evaluation function is evaluated for every node on the frontier. And based on that evaluation function, we choose which node to expand. So now, since we know what we are trying to do, which nodes we are expanding, can you tell me what is the evaluation function for breadth first approach of this tree search?
I guess it must be something that takes us ahead. So
yeah, so what will be the value of Fn?
What would be the?
How we compute it? How is the computational approach to calculate, to define in a breadth first approach, what is the evaluation function?
The node from which we start, the depth of, we can calculate some sort of depth.
Current node.
From that node, how, yeah.
Current node to the frontier node. Just the distance between the current node to the frontier node is the evaluation function. So essentially every node on the frontier has an evaluation function value equal to, has the same value, which is equal to 1. Right? If we treat just the evaluation function to be equal to 1 for every single edge. So now every frontier node is connected to the current node by a single edge. Therefore, the evaluation function returns 1 for every node on the frontier. So in other words, the evaluation function is just the number of edges between the frontier nodes and the current node. So if we define the function this way, automatically the breadth first approach will be implemented if we write a code based on this evaluation function. So in that sense, if we define evaluation function correctly, automatically breadth first or depth first or other approaches that we'll mention, they will be implemented by simply changing the evaluation function. So second point that we also discussed earlier was whether this method is suitable for infinite state spaces or not. So we just confirmed that it guarantees a solution. So it is finite space or infinite space, it doesn't matter, because practically all possible paths are searched and no solution will be missed. And it can be implemented as FIFO queues, first in, first out. And then it will return a path with minimum number of actions. Now here we have to distinguish the number of actions and the path cost. Are they same?
So can you repeat the question?
When we are saying the minimum, we ensure that we are expanding the nodes which are connected, which are at equal distance or which are at a unit distance from my current node. They're the frontiers. So in the end, we will find the best solution where we have reached the goal state. So once we have reached the goal state, the path that has been found now to reach the goal state, does it guarantee a path of the lowest cost or the path of the lowest number of actions? Here, I want to distinguish between the number of actions and the cost. And that will define another algorithm. Can you guess what is the difference between the cost and the number of actions? Is it the same?
No, minimizing the number of actions would mean that we do very less actions, even if though the cost of each action is very large.
Great.
Minimizing
Yes.
cost would be we can do many actions, but the cumulative cost should be yes.
So the best solution that this breadth first approach will find will be best cost path or the best action path. Is it possible that the breadth first finds a solution which has the minimum number of actions, but does not have the lowest cost? Is it correct? Of course, as you said correctly, that each action may not be of the same value, same cost. Some actions may have a higher cost than others. But here when we are searching a tree or a graph, we are not really incorporating that cost into the model. So is it possible that breadth first ends without having found the lowest cost path?
Yes, sir, that is actually possible.
Yes.
Like you choose a lot of things, but you may not get the optimum path, so that may
Yes.
correspond to higher costs.
Yeah, because it is just counting the number of actions. It is not assigning any weight or any cost to that. That action, since it is just looking at the connectivities, these connections may be very expensive. And by just counting those number of actions, it might have reached the goal state. But it is also possible that there were other paths which had smaller cost, and they could have been reached to the same goal state, and the same goal state could have been reached through that path, which has not been explored yet, because the breadth first search has stopped. All right, you understand this point? Everybody gets it? Pushpak, Priyanshu, Tarala, Umesh, who are on my screen. Can you all understand this?
Sir, I need a bit more about why this has minimum number of actions and lowest cost. I figured out a bit, but could not clear myself enough.
Okay, I'll give you an exact instance in my next slides. But right now, I just want to emphasize the fact that every action does not have an equal cost. And because the number of actions and number of costs are two different things, therefore, this method is suitable to reach a path which has a minimum number of actions to reach the goal state. So it will guarantee a solution, but it will not guarantee that the solution that has been found is the best solution. That is the point we have to make. So the minimum number of actions correspond to lowest cost only if the cost of every action is 1. That is the last point written on this slide, and I will elaborate this. And that is why actually there is another algorithm. So actually, it is just an illustration of what we said. You expand the root node first, you start the initial state, identify the successors of this node, define a frontier, expand all the nodes on the frontier, then for each node, you repeat step 1. This is the whole thing. Now, this has been demonstrated in this figure for a binary tree, which is easier to understand, that every node is connected to, what is the binary tree? We'll come back to this question. I'm not forgetting this question. I'm coming back to the question that we just raised. But in the meantime, yes, what is the binary tree?
Yeah, every node has yes then or equal to 2
children. Yeah. Yes. So every node is connected to two nodes. And this, if I want to search something which is there down on the tree, somewhere down, which is a goal state, then exhaustive, it will kind of implement an exhaustive search, and a goal state will be confirmed to, will be ensured has been reached. So this is just an example of what we have already discussed. So starting with A, you go to B and C first, and from B you go to D and D first. After here you have reached D and D, you do not expand D and D, you will expand C first. That is the main point, how it how it differs from other approach, which is called depth first approach. I'll come to that. So, but it will go to B first, and then from B, D, and then F, G, and so on. So I'll go to the next point then. So these are the points that we have to consider about this method. We discussed what is a binary tree, uniform binary tree. What is a uniform binary tree?
I guess in which every node has exactly 2 children except for the Eve nodes.
Yes, right. And also the action cost is 1 in each case. If a binary tree is uniform with B successors at each node, so yeah, so how many nodes will be traversed for a depth T? Can you count this? Depth D, you understand what is depth D? Is after D levels. Oh, you can't hear me?
No, it's okay, sir. We can hear you right.
Okay, okay. Yes. So the question is, the first question we already we discussed, what is the binary tree? If your binary tree has uniform, is uniform, and so that every node has B successors, then how many nodes will be traversed when depth is D?
So B raised to D.
Say again? B to the power D or B into D?
B raised to D.
I'll explain this. I mean, this is close, but not complete. And then next question will be, what is the space complexity? And then we will discuss what kind of problems can be solved. So in the next slide, I have the answers to these questions. So number of the paths to be traversed at depth D is actually 1 plus B square. In the first stage, you cover B square. Depth is, of course, number of nodes there will be B to the power D. So the number of paths that you traverse to reach there is B square at the level 2, B cube at the level 3, and so on. So number of paths that you have to search in order to reach depth D is this given by 1 plus B to the power, a summation of B to the power I, where I goes from 0 to depth. And therefore, the complexity of this method is B to the power D, the highest value in this polynomial. So if my goal state lies somewhere at depth D, then the number of paths I have to traverse is really huge. And as some numbers for your estimate are written here, when D is equal to 10, typical execution time is 3 hours and 1 million nodes per second. Suppose we can cover 1 million nodes per second, it will take 3 hours to reach the last node. You may be lucky, you might find the goal state very quickly, but we have to, when we look at the complexity, we have to look at the worst case scenario. So in the worst case scenario, you will require 10 terabyte of memory just for a graph which requires 10 depth levels. And assuming that again, 1 kilobyte is assigned to every node. So this is the kind of huge resource requirement that this method has. And at D is equal to 14, then amount of time that it requires will reach about 3.5 years on a single node. So that shows that this kind of breadth first approach is not viable for searching large graphs. This is only suitable for small graphs. Okay, so other question was complexity we answered, and yeah, what kind of problems then? We already made the remark about the kind of problems we answer. Small graphs and well-connected graphs, and also the best for the graphs which do not have the back loops. So if they are directional graphs, that is the best. So we were highlighting the point that we distinguished between the cost and actions, because every action may not have the same cost. Then there is Dijikra's algorithm, which says that you should not expand frontiers by looking at the distance from the current node, but you should look at it in terms of the cost that node has. And you expand the graph in such a way that you have, at any given point of time, you have expanded the nodes with equal cost, not with equal number of actions. Is it possible theoretically to do it? Is it possible to expand our frontier, only those nodes, by the principle of uniform cost instead of uniform number of actions? How would you possibly do it? Can you imagine and explain to me? So it's like, you can think of this. Suppose you're navigating and somebody says, okay, you can go from JNU to Delhi University. There is only one traffic signal on the way. This is the route. So this is kind of, if you take that route based on the number of signals, then you are basically following a breadth first approach and you are counting the number of actions required. But then there is this non-signal route may be a very curved path and may take really a long time. But if you incorporate also certain, instead of going along the curve or along, although there is no traffic signal, there are other alternatives where you have several traffic signals, but they take you, the number of kilometers is less on that side. So in this case, how will I expand? I will just calculate, okay, through the first signal, I have two options. I look at the first signal, that is at say 2 kilometers. And on this route, my signal is at 10 kilometers. And then in the first one, I have a first signal at 2 kilometers, second signal at 3 kilometers, then at 4 kilometers. So I will continue to going deeper along that route where until I have covered 10 kilometers. So when I have covered 10 kilometers, then I will say, okay, and I have another alternative, which is also 10 kilometers apart. So I will expand this node of 10 kilometers after I have covered all the three nodes on that alternative. So this kind of algorithm is the Dijikra's algorithm. And this I have further illustrated here. Suppose I am going from JNU administration, from East Gate, North Gate, IIT Gate, and Bearsarai. I'm just reading here. So this, in the breadth first approach, you will end up going to Bearsarai from this route. In the uniform cost method that I just mentioned, you will end up going to this Bearsarai through this route. In route 1, you are taking just 2 steps. So action cost is 2. Number of actions is 2. But the distance you are traveling in that route is 3.2 kilometers, 3.1 kilometers. In the second model, if I use this approach, that when I reach when I'm here at JNU administration, I will compute the distance to East Gate and North Gate. So this is at the first level, I'm doing the breadth first. So this distance is 1.1, this is 1 kilometer. I'm doing this. So now I have two options now. So in these two, which node to expand first? I will expand this node or this node. In route 2, I'm expanding North Gate node first.
Minimum cost.
Yeah. In the breadth first approach, I have to expand the East Gate node and North Gate node together because they both have the same cost. And then from there, I will find the distance and I will reach there. So I will say, when I expand East Gate, I find that the Bearsarai has been reached directly. From North Gate, when I look at, my goal state is not being reached. So my goal state is not being reached in my, when I reach the depth level 2, it is reached from this route. Therefore, I end up doing 3.1 kilometers. In this case, even though my goal state has not been reached here, I will expand this. I say, okay, my total distance is 1.1 kilometer here. So I expand this. So when I reach here, now my total distance reached from here has become 2 kilometers. The distance reached from here has become 1.1 kilometer. At this point, I will expand both nodes, East Gate and IIT Gate. So East Gate node has the same level as IIT Gate signal in the second graph. In the first breadth first approach, East Gate has the same level as the North Gate, but it has a lower level than IIT Gate signal. Therefore, when I search the Dijkstra's method, I will be able to select route 2. But if I use it breadth first, I will be able to select the route 1. Is this example quite clear to you? And this answers your question that you were asking earlier. I think Pushpak was asking. Can you see this choice that breadth first is giving me route 1 and uniform cost is giving me route 2? And which is better, breadth first or uniform cost, which is giving me a better navigation route?
Yeah, route 2 is.
Route 2 is better because it is actually counting it is actually calculating the cost, and it is expanding the paths. So second method, uniform cost method, is guaranteed to return a path with minimum cost. Breadth first approach is guaranteed to give me a path with minimum number of actions. That is the key difference between the two approaches. All right, any question on this? Okay, I go further. So in the uniform cost approach, the complexity is actually measured in terms of the cost of optimal solution and epsilon, the lower bound of the cost of any action. So there may be many actions. Some of them may be low cost, some may be high cost. And what is the lowest bound of any actions? That is, suppose epsilon. Then the worst case complexity for a binary tree with B successors will become B1, which is the B to the power 1 plus C star divided by epsilon, which is kind of estimates the number of actions associated to a given cost. So this is how we calculate the complexity of uniform cost search. Okay, now the other extreme of this. So uniform cost just incorporated a kind of reconcile between the number of actions and the cost. Now, still, there may be another approach. So what is the problem with these two approaches that we have just looked at? Uniform cost, Dijkstra's method, and the breadth first approach. When do you think, I just discussed what kind of problems can be solved with this? So when will you think the breadth first approach or the Dijkstra's this approach, uniform cost method, when these two methods will fail? Or on what account will they fail? So we have earlier seen what should be our benchmarks for looking at a good method. So this was, if I go back here. So you look at these 4 criteria for any method: completeness, optimality, time complexity, and space complexity. So now that we have covered 2 aspects, the 2 methods, one the breadth first method and the other the Dijkstra's uniform cost method, or which is basically a variant of the breadth first approach. So which of these 4 criteria will be
Space complexity.
Space complexity will be the problem, and also the time complexity, because you have to do a lot of computing. So in terms of the complexity, this will fail. But as far as completeness is concerned, both these methods are complete. As far as optimality is concerned, these are the solutions will be found. Although the optimality is defined slightly differently in the 2 methods, but optimal solution is guaranteed to be reached. But in terms of complexity, both these methods fail. So the alternative to this, therefore, is to be searched, and one of these alternatives is the depth first approach. So what do we do in the depth first approach? Can you guess now? I think the term should be self-explanatory. Can one of you guess what would be the depth first approach?
Sir, we select a node and then we go on until we reach the destination or the endpoint, and then we backtrack until the first diversion, and we go on.
I think you understand. We go on means has to be explained properly. What do you mean by going on? In breadth first also
reach
we are
the
going on.
we reach the optimal state, but in depth first we choose a supposedly a node and then select its one of the neighbors, go on finding the final state, or if it ends without giving a final state, then come back, choose the another one in the first divergence.
No, you understand the depth first, but you are not explaining it correctly. Maybe you have to rephrase it. So let us define it in these terms. So I am at the current node and I have the frontier nodes now. Suppose I have 4 frontier nodes. Now how do I apply the depth first method? Yes, Pushpak, can you complete your answer now here in this?
Sir, I'm trying to actually phrase it the right way.
Yeah.
Take a minute.
So it is written here, but let me show this figure later. I go back to the older figure, and on that figure, let us map the depth first approach. So just if you can identify the correct order of nodes, then I think you understand the depth first model. So from A, what are the nodes to be expanded?
Just pick any of the 2 nodes.
No, A is connect. Frontier nodes are B and C. So which one should I expand?
Anyone could be expanded.
Okay, let us say I expanded B, and then
Again go with the D or E, any one of the D or E.
yeah, after B, we don't go to C. That is the key point here. Between B and C, we can decide maybe some other criteria how to choose nodes which are at the same depth.
So
Because
it is the difference now. In BFS, we were storing B and C, but in DFS, we are not storing like C.
No, so when A is connected to B and C both have the same depth. So both B and C should be evaluated. After evaluating B and C, then we go to B, let us say, and the B is the first node based on some criteria. The question is which one we choose between B and C. There may be some other criteria. Let us say we chose based on that evaluation function to B. And now from B, I expand to D and E. And then again, I choose D or E and then keep on going in along one branch. So I do not go to the other branch. I keep on discarding other branches and just picking up one branch at every step, which is basically going deeper and deeper without having explored the entire space, right?
And at each node, where I think we will return the minimum cost path in the DFS.
At each node?
We will return the minimum cost path.
Yes, but does it in the end, if you have reached the end from depth first approach, the first question to be asked is, are we guaranteed to find a solution?
Yeah, it is guaranteed.
How?
Because we are expanding almost all the nodes.
If we just go in one iteration, we might reach the end state and the goal state may not be encountered in that. So after B, D and all, how will you go? Yeah, that's a good answer. In the infinite graph, we may not be able to reach the final goal state, but if the graph is finite, yes, because what we will do is we will start from A, we will keep on going deep here, but we don't end after that. We will reach a point where all the nodes in the directional tree have been reached. Then we will come to C, and then we start expanding this. Then we'll come to other connections that were present with A, but they will come after we have done this. So in this, essentially, we search the entire graph, but what is the advantage over the breadth first? Here also we are searching all the paths. So here is the illustration of what I just said, but I didn't show you earlier so that you could explore yourself. So from A, you go to B and C, then from B, you expand to D, and from D, you expand to H and I. And then again, after that, you go to I, and then you keep on expanding. So in this way, you keep on doing it. Okay. So what is the advantage here in comparison to the breadth first approach?
In DFS, we will be able to find the node which is minimum cost, the goal state.
Yeah, Karthik has written the answer. And yeah, so the main point is, yes, that this does not require to store such a large frontier into memory. And it is not expanding all the frontiers. So it is not the memory requirement at every stage is not going b to the power d. It is actually kind of just the length that has been covered in that path. So in terms of memory, it is very efficient. It does not require a lot of memory. And if the space is tree-like, then the method is efficient and also complete, because it is not going back to the path that has been traversed. Therefore, it is complete in the sense it can find the answer. But if the graph is cyclic and there are some back loops, then you might end up being in the infinite loops. So it is not suitable for cyclic graphs and even acyclic graphs where there are repetitions, and because many redundant paths will be searched in this process. So it is not suitable for other complex graphs. But if it is just a tree-like space, then this approach is very efficient and can reach the goal state faster than the breadth first and with less minimum memory requirement. And memory requirement is low because the third point on this slide is because you do not have to maintain a record of the reached nodes table, and the solution can be fast and efficient for most of these searches. These points, third and fourth, last 2 points of this slide already covered. So now we looked at the 3 methods. So backtracking search can be done, as you already pointed out, that once you have this memory, you can backtrack, because like we showed how we do the best first approach, that in the best first approach, we keep the backtracking information and we can backtrack the graph. But so now we have 2 extremes. One is the depth first approach, one is the breadth first approach. And the Jikistra's uniform cost model is also some kind of variant of the breadth first approach. And we saw that there are limitations. One is very memory efficient, and but it may take it may fail in some cases, and it may be trapped in the local loops if we are going depth first approach. And the other is very memory intensive. So a solution would be something in between. So how we can combine the 2 approaches? Can you find your own innovative way that I have a breadth first approach and I have a depth first approach? Can I combine these 2 in some way? Can you suggest something to combine these 2? These questions are aimed at exploring your natural intelligence without having read. Can you yourself guess how do you combine the 2 approaches of depth first and breadth first? If you can answer this question, so probably you would be able to make this kind of discoveries in the future yourself, when some solutions are known and you will find new solutions.
So are we trying to merge both of them or looking for the optimal?
No, trying to
optimal way of these?
combine a method which uses depth first to some extent and breadth first to also to some extent. So how can we create a hybrid method from these 2? Think of this like this. Suppose you are in a ground and there is somewhere where a treasure has been reported, that this ground has some treasure, and you have specific points where you can search them. So you can just dig up to 1 meter at one point of time, and then the treasure may be located at 100 meter or 90 meter. You do not know how deep is the treasure. So, and you are given a space to search. So if you do the breadth first approach, what you will do is you will go 1 meter, 10, whatever is the possible distance that you can do in one step. You will do first level search, all possibilities. Then you have dug up to say 1 meter, and then you go from search again, another 10 meters. then another 10 meters, and another 10 meter, and so on. This is like a breadth first approach. And what will be the depth first approach in this case? You are on one side, you keep digging down and down, down, and keep some upper limit. Let us, or until you have reached the center of the earth. So whatever method, you keep going down and you ensure that there is no treasure in this particular location. Then you go to the next location, then you go to the third location, and so on. That is how you scan. So these are two extreme approaches. Now, looking for this gold hunting, can you tell me how would you do it as an intelligent person? You got my question? Have I phrased my question correctly? Just
Sir, if it is about a person, like we can do something, if you go 100 meters deep, go that much deep, you find nothing. So you just go on the same level again, some say 10 meters, you find nothing. So you just come up.
Yeah. So instead of doing it, yeah, right. Excellent. So this is what I expected you. And that is what is actually done. So instead of going deep until infinity, you set some limit for yourself. You say, okay, up to 10 steps, I will search in one location, then another 10 step in another location, and so on. And then you create your optimum kind of range in which you are going deep. And in that range, you are going also broad. So you are in that way, you are exploring the breadth of the ground also, and you are exploring the depth of the ground also. So you are not exploring the depth until the lowest bottom of the location at every place. So that is how you're combining the two. I think that is how we do in our life. That is how we do most likely, right? There are people who keep on trying to the solution and going deeper and deeper in one thing. There are people who will try to explore everything in a systematic way, completing the entire wavefront. And there are people who will do a mix. So most people will probably in our lifetime, we try to use a mix and match approach, and we try to explore things to a length, and then we try the other to a length. And we might have different parameters to what extent we go deeper in one location. And then, so in real life, if somebody searches for things like this, they adopt this approach. Nobody approaches a depth first approach or a breadth first approaches. Very few people will use any one of these approaches. But in general, in our life, whenever we are encountered with these problems, we use a mixture of these two. So that is what is used. This is iteratively deepening approach is one, where you deepen iteratively. So you're doing an iterative approach. You put a depth limit. Then within that depth limit, you are searching the entire breadth. And then you increase your depth limit again. You go to the next level of depth. So it is not every step you are doing the breadth search. You are going deeper. So that is how you can reduce the complexity also. And you can also take the advantage of the depth first approach. All right, you understand this? How do we use the iteratively deepening search, which is a kind of an approach, which is mixture of the two. And the whole point is to do depth search within the breadth, or do the breadth search within a depth first, and then next level of depth. All right. So this is bidirectional tree. So,
but this method may or may not be guaranteed that we will be able to reach goals.
No. If the two methods that we discussed are guaranteed to reach, eventually you are searching everything. It is just you may take longer to find out. Like the depth first is not guaranteeing that your best solution will be found the fastest manner, nor does the breadth first do. So, but if breadth first approach can give us a solution, and if the depth first can give a solution, this can also give a solution. So in that sense, they're not different. It is just about which is searched first. So this is the comparison. So some of these I have covered, some bidirectional I have not covered. So you can check it later or do it yourself. So this breadth first approach, uniform cost approach, depth first, and depth limited and iterative deepening. These approaches, are they complete? Depth limited is not complete. Because why it is not complete? Because breadth, we are limiting how far we are going. We are not searching the entire breadth. That also is limited. And the main point is that this is not give us the optimal cost, because the cost has not been implemented. And then time complexity is written here. So you can look at this comparison table. And this is taken directly from that book that I've been referring to. Okay, so we stop here for today. Any more comments or questions?
So that was depth limited or breadth limited?
Basically depth limited, but breadth will be, as I said, so we just say, okay, up to 10 edges deep. So up to 10 edges deep, you do the entire depth, entire breadth, and then next 10 and next 10, etc. So also, since you have to do it in a finite way, you're not going deeper into this. So breadth also will have to be fixed, but that fix is a kind of a parameter within which you are searching it. But it is called depth limited because the depth is fixed. But if it is, for example, an infinite graph, so for an infinite graph, you have to define the size of the breadth. All right. So if there are no more questions, I'll stop here for today. And for the agent modeling and the graph search, I think we have covered what we wanted to. In the next few classes, I'll take a view on the machine learning aspects. And for that, I will first start with the understanding of what learning is in terms of human learning. Same approach that we adopted for AI, same approach we'll adopt there. We'll look at a few questions of the theories of learning, and then we'll see how they are incorporated in the machine learning, so that the paper, this course will be slightly different from your traditional machine learning course, but the motivation for the machine learning and how learning. So one thing before we motivate, and I'll repeat this in the early stages of the next class also, is that so far, whatever we are studying in terms of agent-based modeling do not require learning. They require basically an understanding how to find the best solution. So it is a problem-solving approach that we have taken. They are not data-driven approaches. They are just theoretical and theoretically sound approaches. Once we have formulated the problem as a graph-based approach, or as we call that, the standardized problem. So once the agent has defined a standardized problem, many real-world problems can be solved according to that. So they do not require prior data, whether this method was working or not working. They are just intelligent methods without having to do machine learning. So learning is another aspect of intelligence that is incorporated into the methods. And then in the next class, we'll start looking at what learning is and what have people studied about human learning, and then how it inspires the computational methods of learning. That is how we'll proceed in the next class. Thank you for today.